So, welcome to this session, everybody. I am continuing in my series of lectures on thrilling search of fundamental particles of matter. Since we are meeting up after about 3 4 days, so let me just give a quick reminder. Mainly, the outline of talk is going to be classification of elementary particles, symmetries, and their consequences, and how do we describe symmetries with the mathematical apparatus known as group theory. And then I hope, if time permits me, I will apply these internal symmetries, especially for the hadrons, and how it leads to quark model. Otherwise, I will continue further in uh, in further lectures. As a quick reminder, we have seen that elementary particles can be broadly divided into category. One is the matter particle, the other is the quanta of force responsible for various four fundamental interactions: electromagnetic, weak, strong, and and gravity. So photon we need as a exchange particle for the electromagnetic uh, interaction, whereas three W's, W plus W minus Z0, weak bosons, are required for mediate weak force. Eight gluons are required for strong interactions, especially at the quark level. Graviton situation about that is a bit uncertain, but otherwise also we don't include gravitational interaction for particle physics. So I'm leaving that aside. Higgs boson is a typical particle which is required to produce mass to the all the massive particle. On the matter particle side, these can be divided into families, leptons and hadrons. There are six leptons which are point-like up to the present energy scales, and the hadrons can be divided in two families, mesons and baryon. These are some of the names, but they are really very large in number of several hundred. Obviously, these are not the fundamental particle, so they are supposed to be made up of quarks, and we need six quarks in all. Each quark appear in three three color. So this is just a table of leptons. Electron, it's neutrino. Muon, it's a neutrino. Tau lepton, and it's neutrino. And obviously they have mass. And initially people thought that neutrinos may be massless. Still, we are not very sure. But at least mass oscillations, neutrino oscillations which have been observed, that indicate they do have mass. But what is the true nature of mass, and can we determine it? These are again issues not properly settled. However, what we see is that there are three charged leptons and three neutral. All of them carry spin half, and they also carry separately the lepton numbers, which are three in kind: electron number, muon number, and tau number. So this is the opportunity where I can say that all fundamental particle, elementary particle, they carry lots of new quantum number. So here what we are seeing is these kind of numbers. Then as far as hadrons are concerned, even as early as 1965, lots of mesons, you see here the spins are given, spin 0, spin 1, spin 2, spin 3, even up to spin 4 particles. They carry certain parity. Also, there is this zoo particle we don't have to remember, except the first fuse, which I will talk. Similarly, for the baryons also, we have large number of baryons carrying spin even up to 15 by 2 in, of course, units of H. Then we have sigma and xis and also omega. Of course, this is the situation before 1965. Obviously, after that, lots of new particle called charm particle, bottom particle, and so on. They are also seen, and many more will be coming. So this hadron Jew and meson Jew certainly seem to indicate that probably these are excited states of lighter ones. We will see these things. So as far as the hadron family is concerned, there are a couple of hadrons, hundreds of them have been seen, and seem to have baryons seem to have spin starting with spin half h. So they are fermions. They up to 15 by 2 certainly have been seen. And similarly, mesons with spin 0, 1, 2, 3, 4 have been seen. Most of these, particularly these heavy ones, these high spin ones, both in meson family and baryon family, decay quickly through strong interaction, whose lifetime is of the order of 10 to the minus 23 seconds. So, however, lower spin states, especially spin half and spin zero particle, they decay weakly or electromagnetically. The detail of this, maybe I will be able to talk some other time. But here, what I am going to think about is that how to understand a pattern which these hadrons show. But we find that mesons, once you fix their spin and parity, this is again, I should remind you, situation is around 1960s. So at that time, they were forming like octets or singlet. Similarly, baryons seem to appear in multiplet of 8 and 10. So this octet behavior was very crucial and attractive. This shows that there are some patterns or symmetries behind them. So that is what we will explore. So this talk is going to be a little more technical, as Professor Shastri asked me to go into the details of symmetries, how to describe them. So let me first remind you that symmetries are very important and they are present everywhere, even in classical physics. But I am limiting my discussion for quantum quantum theories. So what we find here is that symmetries are responsible for degeneracy. That means two states have same mass or same energy if they're bound, and this degeneracy may be exact or often it is approximate. Then these symmetries are also responsible for various conservation laws. These conservation law can be divided in two categories: external and internal. Like conservation of energy, momentum, angular momentum, even parity can be called external conservation laws, whereas the conservation of charge, isospin, and many such like lepton number, baryon number, and so on may be called internal conservation laws. And finally, very importantly, but I will not talk about this in this series. When I will talk about fundamental forces, at that time I will show how symmetries dictate even the dynamics. Why Coulomb law should be like that? Actually, when we learn first time, we hardly question this from where this has come. It seems to be, of course, empirical, but is there a reason behind it? That we will study when we go there, and it is a consequence of so-called gauge asymmetry. So if you're smart, you can have some immediate connection with the gauge gauge transformation of Maxwell equations. Anyhow, I will first show you how these symmetries lead to degeneracy and conservation law. It's very simple problem. Any student who has learned quantum mechanics, in fact, can do it. So let us take a quantum mechanical system. I had actually discussed this last time also, so I will go a little fast. So let the Hamiltonian H describe a quantum mechanical system. What do I mean by that? You will have a eigenvalue problem, and the eigenvalues of this operator Hamiltonian gives you the energy of the state, and size are the states which we have to find. We can choose any picture, Schrodinger wave mechanical picture, or even Heisenberg matrix mechanics picture, no problem. Now, what we see then, there are not just one states. Often we find that these eigenvalue problem have many energy eigenvalues corresponding to different eigenstates of the same quantum mechanical system. So consider a symmetry operation which is associated with unitary or orthogonal operator. This is what I will elaborate more very soon in the next towards second or third slide. So we restrict to unitarity, which is U dagger equal to U inverse. U dagger is called U adjoint. That means we are performing, suppose we are dealing with the operator in the form of matrices, then dagger means complex conjugate of transpose of a matrix U. So if that happens to be its inverse, then we say it is a unitarity operation. We will use this condition soon. So this operator U connects, let us say, a eigenstate psi to another eigenstate psi prime of the same Hamiltonian. So that way, this psi prime is equal to U psi. And suppose in the beginning we see that this new eigenstate has a energy eigenvalue E prime. Obviously, to begin with, E prime is different from E. That is what we will say that they will be the same provided a Hamiltonian or quantum mechanical system honors the symmetry uh, described by this particular operator U. So how do we say that? If the Hamiltonian remain unchanged under the transformation of given by this operator U. Everybody, I hope, remember here that eigencats transform like this, whereas uh, any operator transforms like this. You sandwich the operator between U and U dagger. It is essentially a similarity transformation. So suppose as we have started with, it is a unitary operator. So it means U dagger can be replaced by U inverse. So that amounts to saying that HU is equal to UH or U commutes with H. So this is the language which we normally use. Whenever an operator commutes with the Hamiltonian of the system, then it leads to degeneracy. How it is there? It is very simple. I already know that the eigenvalue of the Hamiltonian for the old state psi is E. Now I apply the Hamiltonian upon the new, which I know is E prime, psi prime. But what I do, I replace psi prime by U psi here and apply H to it. Now I can switch them because I know HU is equal to UH. So if I do that, then H goes inside and can be applied to the state psi, giving you the energy eigenvalue E. So you end up having UE. Now E is now a number, so it can be taken out. So what we find is EU psi and EU psi is E psi prime. So that immediately leads us to the conclusion that E prime is equal to E, that is degenerate states. So this is a very general result. If an operator U or any operator, any symbol can be used, commutes with the Hamiltonian of a quantum mechanical system which have many states, then those states which are connected with the unitary operator are, are degenerate. Another consequence very important is a symmetry and conservation law. And we know that in Heisenberg picture, this also I discussed last time. Time development of an eigenoperator U is given by du by dt equal to 1 over iota h and the commutator of U with the h. So if U is not explicit function of time, otherwise partial derivative of U may also appear. And now if U commutes with the Hamiltonian of the system, then obviously the right hand side becomes zero and U will be constant of motion. Specifically speaking, the this quantity, which is the physical quantity, expectation value of U between the state psi will be constant of motion. That is nothing but a conservation law. So what we see here that U can play two roles. One, it can act as a shift operator, which will connect one state with uh, with with other ones, or it can be eigen operator itself. If it is eigen operator itself, it will give you the constancy of eigenvalues. That means conservation law. If it is a shift operator, it is connecting different states that will lead to degeneracy of the state, as I have shown. So now, how do we describe symmetry with the help of a group theory? So that is what I did last time also. The group theory, in fact, now every student who has studied NCERT books know very well. Incidentally, they don't use the term group, but whenever we have set of elements, the simplest example is in our integers, real number, complex number, which can be combined with some operation. We usually denote by star, but this does not mean it has to be a multiplication. It can be any kind of operation which can combine the two elements. It can be ordinary addition, it can be vector addition, it can be matrix addition, or it can be multiplication, numbers multiplication, matrix multiplication, or even more complicated objects. More particularly, we are interested in transformations. Say for example, uh, rotations. Anyhow, so any a group is nothing but a set of elements which, under some operation, satisfy the following four postulates. You can call it. Some books say axioms, or some simply say them. Properties. All mean the same thing. First is closure. It means that for any two elements, x, y in the whole set, we pick up them, any two elements, and when we combine them, then result also belong to the same set. Then associativity. Suppose we want to combine three elements. Since we know the procedure of combining only two elements, we have to go in in steps. So either you first combine x and y, and the result is combined with z, or you combine y or z, and then you combine that with x. Result is same. So this is associativity property. And identity means there is an element, specific element, unique element E. E is just a symbol in G, such that when you combine that element with any element of the set, you end up with the same element. So E star X and X star E is equal to X for all X in G. And then the inverse, for every element X in G, there exists a unique element Y in G such that X star Y or Y star X is equal to identity. And then we can say Y is the inverse of X. I'm sure in sixth, seventh class, or even early mathematics, we all have actually studied these things. The only thing is we don't use the name group at that level. And incidentally, also notice I have not included commutativity, though it is very common for number multiplication and additions, because that is not essential to define a group. However, if commutativity holds true, we call it is a commutative group. If it does not hold true, we say it is a non-abelian group. Examples are simple. Again, the real number, complex number, even vector under addition are they obey the commutative behavior. Whereas if you multiply matrices in general, they don't obey the commutative property. They often form non non-commutative group. In order to name a great man, Abel, who contributed great deal in group theory, we call commutative group abelian group, and non-commutative group non-abelian group. So that is examples, as I have said. If you have not done these things before in school days, you can do now. You can show that a real number under relation form group. Same thing is about vector. They may be two-dimensional, three-dimensional in general, and n-dimension. In fact, you can also take m cross n matrices. Uh, we should choose matrices of the same kind. They form group under matrix addition. But I am more interested in square matrices, n cross n type. Obviously, we have to choose non-singular. It is very simple because otherwise inverse will not exist. So n cross n matrix is form group under matrix multiplication. In fact, if you have not done this problem before, it's a good time to see and convince yourself that in general, all n cross n matrices which are non-singular, that means their determinant is not not zero. They form group under matrix multiplication. So, my friends, you can take it as an exercise. However, their specific role is going to come when we talk about group of rotations. Say rotations of vector in two-dimensional, three-dimensional. You can also increase it to any n like dimension. In fact, these rotations, how do they form group? What is the rule of combination here? Rule of combination is very simple. After applying one rotation, you apply the second one. That is as simple as that. So how do we use these things? First of all, there's a little technical information. In general, we call Lie groups. These groups have continuous transformations. And the rotation, which I will specifically talk now in the next slide, they are special cases of Lie groups, which are which we need in order to understand various patterns of the elementary particles. So these are very good examples, and I'm sure everybody will enjoy them. They are not difficult. So let us remind ourselves. This is again a class 7 material given in NCRT uh, mathematics book at +1 level. So here we find, suppose we rotate a vector whose components were x1, x. Now we actually rotate it by angle theta, and it now acquires the new components x1 prime and x2 prime. It is a simple trigonometric exercise to show that x1 prime becomes x1 cosine theta minus x2 sine theta, and x2 becomes x2 prime, which is now x1 sine theta plus x2 cos theta. So interestingly, notice that this rotation matrix, which is being used as a transforming matrix, satisfy these condition, orthogonality condition. That means its inverse is nothing but its transpose, and they are special in the sense their determinant is one. It is very trivial because determinant of this is going to be cosine square theta plus sine square theta, which is always one. However, we can write down these two equations in a compact form, which can immediately be generalized to other higher dimension one. But just as a remark, see, that is how why then the name of the group is SO2, special orthogonal group in two dimension. You don't have to be afraid of these words, as I've already explained them. But for the sake of simplicity, if you look at the books, they sometimes write as a R2 group, that means rotation group in two dimension. But as I said, in compact form, these two transformation equation can be put like this. So we have xi prime, and it is given by a linear combination of old components. So these Rij, these matrices which are representing rotation, they are forming group. So this is what we have to say. And this also I talked actually last time. My friends, younger friends particularly, can take this as an exercise that these kind of matrices satisfy closure property, associativity property, and there is identity when you choose theta to be zero, and theta uh, when you replace theta by minus theta, you do get the transpose which acts as the inverse of this. So this I did, I think, last time. So I'll jump over this. Then when we go to a rotation in a third dimension, first of all, what I am doing, I am writing that equation which I put in the last slide, that new components are given as a linear combination, the old one. The difference is here we have a summation from j equal 1 to 2, and I also run over 1 to 2. But here ij will go from 1 to 3, and j is repeated, so it is being summed over. And just recall simple rotation in which we have learned in classical mechanics, Goldstein book, and follow XYZ action notation given in its appendix. Arbitrarily, three-dimensional vectors can be rotated. However, arbitrary rotation requires three angles. There are different ways of choosing those angles, but in XYZ rotation, we first transform about the z-axis, then transform about the y-axis, and then finally we then rotate about the x-axis. A combination of all three, that is product of that three, will give you r. So this rij now require three angles. Remember, in case of two-dimensional rotation, only one angle was sufficient. But obviously, since all of us have learned Euler angles in classical mechanics, we know that for three-dimensional rotation of vector, we need three angle. And since each of them they follow the orthogonality condition, so their product would also obey. That is why the name of the group is special orthogonal group in three dimension. So now something important, because probably you know from classical mechanics again that you can see a derivative to be the generator of space translation and time time translation. And I'm sure many of you must have done this thing for rotation also. Suppose I limit first to z-axis and I perform like a rotation of a vector with component x1, x2, x3 above which go to x1 prime, x2 prime, x3 prime related in this particular way. Then for infinitesimal rotation, then this matrix gets simplified to this. It is nothing but identity plus some leftover. And by the way, limiting to infinitesimal, I mean, the rotation cannot harm our generality, because all finite rotations can be obtained by having a large number of successive infinitesimal action. These the rotation. With that, life becomes easy, because this is a simple exercise in Taylor series. So suppose you apply this operator u upon some function of r. You don't have to say it specifically, the quantum function which we are using here. But in general, you can choose some function f r of r. It becomes a function of r prime, and it is now related to the old function like this. So this probably I left as a exercise. But suppose now I specifically apply this on quantum mechanical wave function, then what we do, we are familiar with this operator. This is nothing but third component of angular momentum operator divided by h and minus I. So this thing can be replaced by L3 over h. So what we learn from here is that effect of rotation about the z-axis can be obtained by multiplying wave function by this quantity. So this is essentially your rotation matrix upon the wave function. It is constituted out of identity operator plus a small uh, angle about which it is being rotated, multiplied by the third component of the angular momentum. So once you have understood this point, it is a trivial matter to apply it to other rotation about y and z axis. So correspondingly, we will have similar contribution coming from L2 and L1 component, and taking delta phi to be different in all the three direction, we end up with complete rotation in three dimension given by this kind of a thing. So we have delta phi k, Lk, sum over k is there, h. So in this way, what we see here, that angular momentum are operators are acting as generator of rotation in three dimension. So this is very important. because such kind of results are going to be generalized. So what I often tell my friends that group theory is not at all difficult. In fact, all of us who have learned angular momentum algebra, both orbital angular momentum as well as spin angular momentum and even total angular momentum algebra, we are already aware of groups. But this thing really surprises me. Why even books don't talk of the word group. Very few books I have seen actually recently who talk of group theory while describing angular momentum. So if you understand angular momentum algebra, trust me, you know group theory, because exactly what we do in angular momentum algebra, we replicate those kind of things for other internal groups. So let me give a quick reminder again, because this sheet also I discussed last time. So just as a quick reminder that suppose we know that how the momentum operators are written like that, we can write down all components of angular momentum like these derivatives. We can use any notation, either x1, xyz, or 1231. That is not the problem. It is a simple exercise to show that these three components of angular momentum operator obey this kind of commutation relation. That means Lx Ly commutator means Lx Ly minus Ly Lx. This is nothing but IH Lj. And of course, corresponding cyclic term. When you take x to y, y to z, and of course z to x, you end up with three other things. And this commutation relation, this set of commutation relation is called nothing but Lie algebra. So Lie group is formed by by rotations for this case, and this set of commutation relation is an example of Lie algebra. And we know from quantum mechanics that we cannot diagonalize, or we can't treat operators to be eigen operator unless they commute. So therefore, out of these three, only one can be chosen to be the eigen operator. And interestingly, what we find that their square, sum of their square, lxy square, lx square plus ly square plus lz square, also commute with all the three. So I'm sure you must have done these things. If not, please do it. Take this as an exercise, starting with P operator. First of all, construct all these L, and then show that such kind of commutation relations are honored. And then also find a new operator, which is constructed by adding powers of this. And this itself later on I will call them, it belong to a class of operator known as Casimir operator, which are usually constructed as sum of scale and higher powers of of generator in general. So where I have gone other two operators Lx and Ly. What do? We construct their combination of this kind, Lx plus ida Ly, or Lx minus ida Ly, and we call them L plus minus operator. We will see that they will act as the shift operator. And they are also known as raising and lowering operator, because when we see that we have lots of states, then L plus minus will take us from one one state to another. So this is again what is the utility of this angular momentum algebra, that total angular momentum has this the third component and total angular momentum have certain eigenvalues, and correspondingly they have eigenfunctions. In order to appreciate that, there are many ways. When we learn these things first time when we solve hydrogen atom, or one can directly go to this kind of a thing. So either you start with the del square operator and write down that in spherical harmonic, these I mean coordinates, and or you straight away take this as a definition. Anyway, what we see here is Lz becomes like this and L square becomes like this, and then these L square and Lz we know eigen operator of the spherical harmonics. So, in fact, this statement is quite general. We will see that for any quantum mechanical system, especially in the case of Schrodinger equation, if potential is spherically symmetric, it is central potential, then angular part is always given by spherical harmonics. Spherical harmonics are essentially nothing but normalized product of associated legendary function and exponential im phi kind of a function. So L square has eigenvalues L into L plus 1. This is just a scale factor. And Lz has eigenvalue mh. So in this way, the quantum states Lm are described with the help of two quantum number. One is the eigenvalue of Lz operator, that is one of the generator, and second is the eigenvalue connected with the eigenvalue of Casimir-like operator, that is L square operator. And we know that if we have solved associated Legendre differential equation, that L can have any integer value starting with 0, 1, 2, 3, and so on, and M is restricted to lie between minus L to L. Therefore, multiplicity of this state is 2L plus 1. And the shift operator also work upon them. The form of shift operator in spherical coordinate becomes like that. If you have not done these things, please take them as an exercise. These are very, very useful thing and they are often required. So if we are able to handle them once for all, it will never give us actual trouble. And then we also learned that action of L plus minus upon these state is either to increase or decrease the M value without disturbing L. So this is a point to be noted. This is just a multiplicative factor. That is why we call them as a ladder operator, raising and lowering operator. So starting with M value, fixed M value, when we apply L plus minus upon them, either we increase M value by 1 or decrease, depending upon the operator we have chosen. So then with this, we come to another group, SU2 group. And why I'm mentioning it, because both we need specifically for the hydrogen atom. In fact, we need these groups even in particle physics when we study quark structure of mesons as well as baryon. And more or less, it is very easy and trivial to learn if we have mastered angular momentum. Otherwise, also when you study matrix form of angular momentum, then we find that we end up with this group naturally, because the restriction is in case of orbital angular momentum, the eigenvalues of L are they start with 0, go up to any integer, but they don't allow fractional value, half, 3 by 2, so on and so forth. But when we have a spin group, those half, 3 by 2, 5 by 2 states are also permitted. That is a natural consequence when we go for matrix matrix treatment of the angular momentum. But the interesting thing is their Lie algebra is same. That means commutation and relation of spin operator, which are say S1, S2, S3, they obey this kind of a thing, which is exactly what we have seen here in this. So therefore, lots of common things appear. So whatever we are saying there also comes here. Mean because these are going to be matrices and they allow 2 by 2 form also. Therefore, the name of the group will be changed. It will go from O3 to SU2 group. This is one and major difference between angular momentum operator, orbital angular momentum operator, and spin operator. Orbital angular momentum generate group O3, SO3, whereas spin operators generate group SO2. And you can also write transformations upon states given by SO2 group exactly the same way as we have seen for the case of orbital, uh, I mean, for the case of rotation. So for this particular group SO2, we will have multiplicity with the actually we will have multipliers with multiplicity 2s plus 1, exactly like 12 plus 1. and carrying the eigenvalues s into s plus 1 for s square and ms for third component of spin. So this S value can be 0, half, 1, 3 by 2, so on. Please take this full stop as comma. It is a typo error. And MS like M go from minus S to S. So that is how the states S, MS are, are connected through this kind of algebra. And here also, because we will use S3 as the eigen operator, S1, S2, they will form S plus minus ladder operator. So this treatment can be applied to any spin. However, choosing an example, suppose we choose electron which has spin half h, then its states half half or half minus half are written in many ways. Either we use this eigencat with eigenvalues S and MS, or we can also use Spinner's columns with the column matrix 1 0 or actually 0 1. And sometimes we use the symbol alpha beta, or very simply spin up and spin down. But when we say spin up and down, these are essentially symbols, and we must know which kind of algebra we want to use for the SU2 group, so that accordingly right description can be used for describing the states. So suppose I choose column vectors. These are not ordinary actually, I mean matrices of simple kind. They don't represent vectors. They represent very different kind of quantity known as spanners. And this 1 0 0 1, which are representing spin up and down state for the electron state, or for that matter for any spin half particle. It could be proton, it could be neutron, it could be quarks, it could be in general all other leptons. So these 1 0 and 0 1 kind of column matrices are representing their two possible states, and they are essentially worked upon with the help of famous poly matrices, which are nothing but uh, spin operators when multiplied by half h. So it is as simple as that. So we have states like that. We have here also. So now we can summarize the whole thing. Whenever we have a group theory, what exactly we do? First of all, we choose either group or we choose a transformation, whatever way we want to start. So once we have, say, obtained transformation, we check whether they form a group. Or we have chosen a group, we write down accordingly their transformations. And then we look for the generator of transformation. In fact, game of obtaining these generators from the transformation or transformation from the generators can be played in both the directions. So if you know generators, you can construct the transformation. If you know the transformation, you can also obtain the generator. So once we have obtained generators of the transformation, for example, in our case, we had started with with the rotations which were generated by angular momentum operators L1 to L3. Then we construct a Lie algebra. You don't have to be afraid of that. As we have seen them, what we do, we look for all possible commutation relation among the generators only. So there are actually situations when a number of such generators are quite large. So there is a possibility in our case, what we find only one of the the generators L1, L2, L3 could be could act as an eigen operator. But in bigger groups, there is a possibility of two or more than two eigen operator from this set of generators. Anyhow, we have to find out all kind of commutation relation, and then what do? We identify which of them are eigenoperator, and then the remaining one, which will always be even in number, they will form set of shift operators, like here L3 and L plus minus. And after that, we construct sum of squares, even cubes of such operators, and construct new operators called Casimir operator. In our case, it was L square. And then we look for the eigenvalues of the eigenoperator, say I3 here and Sk here. And the eigenvalues of these eigenoperators are used to construct the states. So these are used to designate the states. So in this way, we enter with the states which have certain eigenvalues, and those eigenvalues belong to the either the eigen operators belonging to the generators or their higher power combinations like L square operators. These two I can leave at the moment, but those who already know angular momentum algebra variable, they also know about addition of angular momentum states. So when we add two angular momentum, say spin S1 and S2, then the total spin can have the lowest value S1 minus S2 mod, and it can go up to S1 plus S2. And then we write down those states as a linear combination of the initial states, and we have kind of CG coefficients. Those CG coefficients are essentially coming from the Lie algebra, that is computation relation of the generators, and they are very useful because that is what we need when we apply perturbation theory to that axis. If you don't understand these 2 points for the moment, you can forget. Now let me illustrate the consequence. This is very important because hydrogen atom is extremely useful for understanding particle physics. Why? Because in hydrogen atom, first time we construct a two particle system which is bound together with the help of some potential which incidentally is Coulomb potential and has spherical symmetry. So whatever we have done now, that is rotation and spin transformation, we can exploit here. But once we have done this, we can do similar thing with more complicated system. For example, we can replace proton by positron. We will have positonium, and that positonium basically bond state of positron and of course electron, though is unstable, but still its detailed spectrum is very much similar the to that of hydrogen atom. Now you can easily replace these electrons and positron by quarks and antiquarks. So all mesons we will see later on can be understood as bound state of quarks and antiquark. So whatever operators we have learned from hydrogen atom can immediately be borrowed to to understand lots of meson in terms of quarks. So that's very important. But the point here I want you to notice is that Hamiltonian of hydrogen atom, of course, for the time being, I'm limiting only with two terms, that is kinetic energy of the electron and of course the potential energy between electron and proton, the Coulomb term. If you start with this hydrogen atom Hamiltonian, which we normally do, we see that it commutes with orbital angular momentum. Very simple, because orbital angular momentum involve essentially derivative with respect to phi and theta, and phi and theta don't appear in the Hamiltonian. So obviously they will come here. So if that is so, then it states having same total angular momentum L, but different third component M value are degenerate. So this is immediate consequence of invariance of Hamiltonian of the hydrogen atom under rotation, or formally called under SO3 group. That is special orthogonal group in three dimension. So 2L plus fold degeneracy is immediate consequence of SO3 group of hydrogen atom. So that's the beauty. But we all know that is not a complete picture, because the true degeneracy, ignoring spin, is not 12 plus 1 forward. It is more than that. It is actually n square. Because if you sum over 12 plus 1, starting from L equal to 0 to n minus 1, that is all orbital angular momentum state for a fixed principal quantum number, we find all states have the same energy, because when we solve hydrogen atom for using the Schrodinger equation, we have binding energy given simply in terms of n square. Actually, it is something like 1 over 1 over n square. So it differs only for different n, but one n has several orbital angular momentum value. So it is just a remark, and I will not go into the detail of this. That actually the symmetry group of hydrogen atom is not just O3 group of orbital angular momentum, but it is actually SO3 cross SO3 group. Those who are really actually curious, I can remind them that if you look at a Kepler problem in again in Goldstein or any good book, it does tell you that besides conservation of orbital angular momentum in classical physics for bound state problems, they also have another set of uh, vectors called Runge-Lenge vector, which are also constant of motion, and they are also three in number. They are basically built up with R and L, etc. So you can take as a homework to see. And the situation there is same here like here, because there we have gravitational potential G mm over R. Here we have minus a square by R. So those three conserved quantity also form another group of the same kind, SO3 group. So therefore, true symmetric group of the hydrogen atom is SO3 cross SO3 group. However, we can leave this at the moment. And then look at the spin, because this group explain only up to the n scale. Then, but the true full actual degeneracy is 2n square. So this 2 is coming from 2 degrees of freedom, which is associated with the electron spin, which is half h. We know its magnitude to be this. So the Hamiltonian of hydrogen atom also commutes with spin operators, because in the Hamiltonian there is no term which will not commute with spin operator, that is s plus s minus s3. So therefore, it's a state with the spin up and spin down should also have the same energy. So this will be the consequence of SO2 symmetric group describing the spin. So in that way, full symmetric group of the hydrogen atom is SO3 cross SO3 cross SO2. This direct product group is responsible for 2n square degree of degeneracy. But is this degeneracy exact? That is the question. Because I'm sure many of our friends here must have handled fine structure and all that, where we find that this actual degeneracy is lifted. So by the way, how do we handle this kind of thing? Again, I can remind you, I have chosen this hydrogen atom as an example here, because similar pattern we will see in when we use internal symmetric group for the hadrons and so on. The picture is same there. Here also what we are seeing here is that we have Hamiltonian, which is commuting with spin generator as well as orbital angular momentum generator, and we find that it gives us a degeneracy, but that degeneracy is often broken because of internal reason or the internal reason. So it means this degeneracy is also approximate. So how do we handle this kind of situation? Because same pattern we will learn in, we will see appearing in the description of hadron physics. So let us recall that degeneracy in a quantum mechanical system may get broken if there is a term in potential term, of course. This perturbation potential term may be arising from external factor. For example, for hydrogen atom, it may be Stark effect application of electric field, or Zeeman effect application of magnetic effect field. So, or it may be because of internal reasons. There are terms which we have ignored for the moment, but they are there. Obviously, we believe that they are not very large in strength. That is why perturbation treatment can be applied. So once we include those things, and incidentally, these perturbations do not commute with the with the unitary operator. What it will do, it will cause splitting in the degenerate energy levels. And how do we calculate these things? As my students, I hope my younger friends have learned degenerate perturbation theory. Then this energy splitting can be calculated using time independent degenerate perturbation theory. That is the standard treatment. And I suppose at some level you have done it. So group theoretically, how do we state it? We say group theoretically that it is the splitting of irreducible multiplet of original symmetry, which is now not honored by the perturbation, into lower dimensional multiplets of a lower symmetry group, which might be honored by the perturbation term we have added. Let me formally actually remind you. If you start with this Hamiltonian of the hydrogen atom, which is sum of kinetic energy and of course the potential energy term, it has this symmetry which we have just learned, 2n square degree of degeneracy, which is described by this group: SU3R, R for Runge length, SO3L, L for orbital angular momentum, and SU2S, S for spin. So these three groups provide the responsibility for degeneracy, which is 2n square. But we all know Schrodinger equation is basically a non-relativistic equation. And when we use Einstein mass formula, the next order term is of the order of V4. I hope somebody or most of you have done this exercise. It is worth doing to expand the Einstein mass energy formula and obtain the next order term as a correction to, I mean, kinetic energy, and apply perturbation theory to that. It is simply the matrix elements of p to the power 4 term between the hydrogen atom state. What it will do, it will break the degeneracy. Suppose I choose an example. Suppose I choose 2s and 2p level. There are two electron in 2s and 6 electron in 2p. Then keeping the original Hamiltonian, we know all these 8 states are degenerate. But if you include relativistic correction, what it will do? It will separate 2s states from the 2p states. So after that, we also know now that electron has spin. As a result of that spin, it will couple to its orbital angular momentum. So LS coupling term is also there. So effect of P4 term is to break this bigger symmetry to lower symmetry. So this we lose, and we have the symmetry group given by SO3 L cross SO2S. But now when we include the LS coupling term, that is magnetic effect, what it will do, it will break this bigger group to SU to J. By the way, J is a symbol for the total angular momentum. And following the spin SU2 group, one can exactly write down everything same, where S is replaced by J. So we have last group which is honored by LS coupling also. That means the energy eigenvalues are described now in terms of N, of course, but also now J. So that will be the, I mean, situation. So the end result would be that 2s half and 2p half and 2p 3 by 2 level will come. This 3 by 2 is actually coming from addition of spin to orbital angular momentum 1. So when we add half to 1, we will have half, and we will have 3 by 2. So the total angular momentum of 2s and 2p will be half, and 2p also will now has actually 3 by 2. So there will be separating between 2p half and 2p 3 by 2 because of this coupling. So the group is now reduced. Incidentally, 2s half and 2p half will remain actually degenerate. Now, if we apply external magnetic field, that is Zeeman effect, what it will do, it will totally remove the degeneracy. So these states now will further reduce to technically called U1 group, but I'm not going to talk about that in detail. Maybe some other time we will take U1 group also, which are very useful. But such kind of breaking, that means a breaking of SU2 spin, may also occur because of internal factor. One immediate factor is the coupling of proton magnetic moment with the electron magnetic moment. So that will give rise to hyperfine fine splitting. So this also breaks this group SU2 S2 for the U1. So with this, we now are able to reach. Shastri, how much time I have?
Sir, I think this is a good
Yeah,
place to
okay.
stop, sir.
Then I
It's
will
already
just talk
5:15.
about this sheet and give until one. So,
Sure.
as far as mathematical apparatus is concerned, whatever we have learned from SU2 spin group, that exactly can be borrowed to understand isospin. So that is why I request my younger friends to do a little homework which I have left, or to prove these things which I have talked about here. Historically speaking, what we see that many of the baryon and meson states, they have nearly the same mass, differing only by a few MeV. So actually, it was Heisenberg around 1932 who saw that proton and actually neutron mass is very small. Mass difference is very small. The proton is 938, whereas this neutron is 939. So they have closely the same mass. So as we have seen that the degeneracy can be exact, it can be approximate. Quite often it is approximate. So same kind of situation Heisenberg saw here, and he thought that there may be some internal symmetry responsible for this near equality of proton and neutron mass. And he was really fond of matrices because he developed the matrix formulation of quantum mechanics. So he applied that algebra to describe, and he called it isospin. Iso simply word means similar to spin, but obviously they represent different degree of freedom. Spin is ordinary spin, which we are actually familiar with. This is something like internal spin, isospin. So what we find later on that many mesons and baryons, they form isospin multiplied and have nearly the same mass. And whatever small mass difference among the member of these isospin multiplied is normally attributed to isospin breaking caused by electromagnetic interactions. So see the similarity. In case of hydrogen atom, electric interaction, that is Coulomb term, honors the symmetry, gives the same binding energy, or the total energy of the state, but it is the magnetic term which break the the degeneracy. So what we find here is isospin symmetry of strong interaction is giving mass, equal mass to proton and neutron, and the small mass difference is coming because of their electromagnetic interaction, because they have different mass. Proton mass is +1, whereas neutron mass is the zero mass. So as far as mathematics is concerned, we use same SU2 group. It is exactly similar to spin angular momentum algebra. The only difference is I have put the commutation relation slightly different. They're same. There I have given one example, and other are obtained as the cyclic term. But this is a very unique way of putting all the three commutation relation three together with the help of Levi-Civita symbol. I'm sure everybody must be knowing here it. When I, J, K, any of them two are equal, then it is zero. So all I, J, K should be different. So it is an immediate thing to see that this set of commutation relation are exactly the same as we have seen before. So there, like spin half, we will have the lowest multiplier to be the doublet, that is a spin up and down, but these are isospin up and isospin down. Corresponding to poly matrices, here also exactly the same matrices we will find will be used to describe the isospin operator. And when we combine these things, we have other representation of the other isomultiplets with isospin half, with isospin 1, with isospin 3 by 2, and so on and so forth. So for example, suppose you look at the table of mesons. We have here k plus k0, pi plus pi0, pi minus eta, and k0 k0 bar. So you can think of this as an iso doublet. They have isospin half with with third component plus half and x minus half. Then pi plus pi0, pi minus form isobacter with third component plus 1, 0, and x minus 1. Eta is isosinglet, and k0 bar k minus again form doublet. And look at their masses, they are quite close by masses. So the only thing is I have put them all together in one, because even though the mass difference between k, pi and eta are quite large, but one can boldly think of putting them together in a bigger group. Maybe we will talk about that actually later. That is SO3. Similar situation was also found for the baryon. See, for example, the isospin idea started with near degeneracy of a proton neutron. Same thing we find for the sigmas also. Sigma plus mass is 1189, sigma zero mass is 1193, and sigma minus has a mass 1197, quite close by. So we have iso doublet, we have singlet, we have iso vector, iso triplet, and iso doublet again. And similar thing happened for spin 3 by 2 baryons, where we have four state forming iso quartet with third component given by plus 3 by 2 plus half minus 3 by 2. And same thing we find for excited states, that is spin 3 by 2, that is sigma star and xi star and so on. Maybe I can stop here. Okay, Shastri ji.
Yes, sir. I think it's a good place to stop. Tomorrow we'll continue from here. I think all of you can just go through these concepts, and if you have any doubts, you can come back with the doubts tomorrow.
Sure.
Okay. Thank you.